This may be the most efficient 49-to-1 transformer that you can build for your end-fed half wave. It has right at 90% efficiency from 80 meters to 10 meters, flat across the band within 1%. We're going to go through step by step how to build this and show you the results. Watch till the end and build one for yourself. Get that power out to your antenna and not going up in heat. We're going to go through how to build one of these more efficient toroids. You're going to have less insertion loss than any other toroid that we've discovered so far to date in the HF bands. It uses a Fair-Rite 264-325-1002 core. It's a type 43 mix. You can either write down this number yourself or use a link in the description where you can get one of these for yourself. We're going to continue to use more of the 16 gauge enameled wire to wind with. This is a little bit more difficult to wind just because the diameter of the hole here is so small. But other than that, it's pretty straightforward. So let's get started on winding this out. We're going to need approximately 50 inches of this 16 gauge enameled wire. So let's go ahead and measure that out. All right, there's 25 right there. Get another 25, and that's 50 right there. Now 3 to 4 inches of this will be for the tap itself, so we can go ahead and cut that off too. There's 4 inches. We'll cut that. Okay, we need to measure about 10 inches from the end of the wire where we will strip off our insulation where we'll be connecting our tap on turn 2. Let's go ahead and mark that, then we'll scrape off the insulation and bend it up and get it ready to start wrapping the windings. You can use a knife, a razor blade, sandpaper, whatever you want to scrape off this insulation. Just get it down to bare copper, just like we did in our previous build, so you can solder to it later. And we're going to go ahead and solder our lead on before we wrap it. It may be a little easier. Somebody suggested that from a previous video. I'm always open to suggestions. So let's try that on this build here. All right, that looks like it's got, oh, there's some more right there. Sometimes it's hard to get the wire twisted around where you can see it and get the insulation off. All right, a little bit more right there, I think. Now, we're going to take our needle nose, put it right in the center where we scraped off that insulation, and then bend the wire down evenly on both sides like that. Gonna crimp it together just a little bit. And now we're going to take and bend out 90 degrees and leave that little loop sticking up, because that's where we're going to do our tap on turn 2. Okay, that's looking pretty good. Get a little more insulation off. I think we're good though, right there in the center where we're going to solder. Should have a good connection. So we'll take this little piece that we cut off earlier and get the insulation off of one end. Maybe go ahead and clean both ends, because it's probably going to be easier to do it now, because we'll need the other end. No, let's not, because we're going to have to cut it to length. We'll wait till we get it cut to length, then we'll strip it off. Enamel's on there good. It is a good insulator. You know, like I said before, this is magnet wire. This is used in pretty much any electric motor, alternator, generator. All right, so that looks good there. We're going to take our needle nose again, bend a small loop in it like that, and we're going to hook that loop right here, and then crimp it over the top of the loop, and then crimp the loop onto the wire. So even before we start soldering, that is a tight mechanical connection, because solder is not a good mechanical connection by itself. But here we've got a good mechanical connection, and we'll have a good electrical connection as well. Get something to hold this in place, and we'll get the soldering iron and get it soldered together. Then we can start our winding. Okay, got the old soldering gun out. This thing, just a few years younger than me. I've had it around 50 years. It does a good job. Let's heat up the joint. Put the solder in from the opposite side. That way the solder will flow through the joint. And we should have a good connection now. Just let that cool down a minute. Okay. Now we got a good mechanical as well as electrical connection there. We can start winding. Just get it right here. Approximate center. It doesn't have to be exact center. And push the wire through. It doesn't matter which direction you go at this point. Just want to get the wire through there. Wrap it. Put it through again. Make sure when you pull it tight that the windings are not overlapped here in the center. And the winding is going to go about halfway around when we start winding the other one. The outside of the windings have to be spread out, because the inside radius is so tight that the wires will get very tight in the center here. So you want to make sure they don't overlap here in the center as you're winding it. So there's our 2 turns for the primary. Get the wire bent up there. All right. So now we'll continue to wind the rest of the secondary. Going to be a total of 14 turns, just like in our other transformers we built. This is a 49-to-1. We went through the math on that in the previous video. If you haven't seen that, you may want to go back and look at that. It's the video just prior to this one. Well, we went through some of the math. But you just have to pull it tight, wrap it around, stick the end through, do it again. Just try to keep from getting kinks in it here. And get it as tight as you can. It's not super critical that it be tight. That's more for our aesthetics than it is for its function. As long as the wire goes through the center of the toroid. That's what makes the toroid and the transformer function, is when it goes through the center here. All right. Bend it up. Keep going. Like I say, we've got to have 14 turns. And we'll straighten them out some once we get them wound. You know, they have machines that do this. I have seen them run before. It is amazing how fast they can do this, you know, on a production basis, and how precise they are. The people that invent those things, it amazes me how they come up with it. Okay, we've got to get a few more here before I stop and count. I think this may be it here. Push that wire on around with your thumb. Let's see if that's not 14, if I measured right. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. One more. Okay, let's see how this is now. Go back over it, make sure I counted it correctly. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, got our 14 turns. We got our tap here at our second turn. And remember, for an auto transformer, the end here, closest to the tap, that is where your ground is connected. The tap will be connected to the center conductor of your coax, which is the center of your SO239 connector here in this build. And then this end will go to the antenna connection. We're going to have to put our 100 picofarad capacitor here. So we'll go ahead and scrape off the insulation here and connect our capacitor. See if we can do them both at the same time, at least on two sides here. That stuff is tough. Doesn't come off. Doesn't just fall off, doesn't peel off. You have to work to get it off. And that's intentional. Good stuff. Almost got it there. Get some on the inside. And on that side there. Okay, I think that's pretty good. Got enough of it off. We can get our capacitor on there now. Okay, this is our TDK 100 picofarad capacitor. Be sure and get a TDK. Look back at, if you haven't seen my other video already, look back and see what a difference the brand of capacitor makes. Get a good capacitor. Don't waste power just because you wanted to save a few cents on a capacitor. Don't make the same mistake I did. I learned from my mistake. And I'm not going to, hopefully not going to repeat that same mistake. Not saying I won't make other mistakes, but hopefully I won't repeat that one again. Okay, we're going to get something to hold that. Let's see if we can't do that right there, just to elevate it a little bit off of the mat so we don't get the mat too hot. Got the leads wrapped around it there. And let's get our soldering gun. It keeps sliding towards the core there. Okay, get a little heat going. Put a little solder on the tip. Then heat up the joint, let the solder flow. Let that cool. We'll turn it around where I can get to it a little easier. Okay, finally flowed. Now, I'm going to put a little bit more there, looks like. Could stand it. Get that solder to flow over there. Now, I think we got good connections. Yep, cut off those excess leads now. And we got a good connection on our capacitor. And what I normally do, you can see here what I was talking about earlier, how tight those windings are there on the inside compared to the outside. You know, the radius is so much tighter on the inside there, so you can only get them as close as you can on the inside. Don't worry about the outside so much here. I'm going to go ahead and get some zip ties and zip tie these in place. I like to do that to secure them so they don't move around on you when you start testing or when you're using them. So put a zip tie through here. And get it wrapped. Pull it up kind of at an angle. Catch that last winding. Pull it tight. Cut off the excess. I'm going to leave a little on it for right now in case I need to pull it tighter. I think I got it pretty tight though. And you can see the centers here are pretty much all tight, touching. As long as they don't overlap one over another, keep them in sequence, it should be good. That's looking pretty good there. Put one on this other side for good measure, just to make sure it doesn't move on us. Get it over the top of that winding there. Pull it tight. There we go. See, that didn't take long at all to wind that. That's a good transformer there. I'm going to go ahead and strip off the ends here. Just scrape off these 3 ends. And I'm going to use one of the previous transformers we built as a template, because this is the same size box I'll end up putting this in. So we've got our 2 connectors here. We need to put it in this direction because this is the ground. Or I'll put it in a new box. I'll put the ground on the opposite side. That way the zip ties won't interfere with the way they are there. So let's just see here. That was about the right length by the time you bend it over and put it to the antenna connector. I'll put it in about the same place on the other one. This one here, since this one's going to the ground, it'll actually go to the shield here first, and then it'll go to the ground. So I'm going to leave it a little long. I'll cut it, or actually scrape the insulation off of it right here in the bend, and then right over here I'll cut it to length. That should be long enough, and I'll scrape the insulation. Probably just scrape the insulation off that whole piece right there, from right there before the bend to right here. And this one here is too long also, so we'll cut it about there, because that's going to go into the center conductor of the SO239 once we get through testing. Okay, we've got our leads trimmed, got the insulation scraped off, and we're ready to connect it back to back with our other transformer. This is one that I built previously so it could have 2 in order to do the back-to-back test. I'm going to solder these connectors together for the antenna and then also for the ground, and then we'll come back and connect it up for the test. Okay, we've got our test rig set up like we did for our other transformers that we measured. We've still got the NanoVNA calibrated, got it connected up in the correct polarity. Here we've got the positive going to the tap on turn 2, and this one is upside down, so this is the positive on this side on this one, and it's going to the tap on turn 2 on this one. We got the grounds connected together. We're going to be transmitting through this one, out through the antenna connection, and back into this one, and we'll be reading how much loss there is between the two. Then we'll divide that by 2 to get out what our loss is for a single transformer, and then we'll put that into our spreadsheet and calculate our efficiency. So let's go ahead and start taking our readings. Here we are at 3.827. We're going to use the same frequency as we did for the other tests, so we'll be consistent. And here we are at negative 0.95. Going up to the 40 meter band, 7.235. Here we are there. That's a negative 0.92. We're just going to go to 2 decimal places. I'll round up it or down depending on what the thing reads. We'll go to 14.267 in the 20 meter band. There's 14.267. That's a negative, see if I can see that here, negative 0.98. We'll go on up to 17 meters, 18.110. There's 18.110, and we're reading negative 100. Going up to 15 meters, 21,300. There's 21,300. Let's stabilize just a second. Negative 0.969, so we'll do that negative 9.7. Going up to 12 meters, 24,925. There's 24,925. That's a negative 0.95. And go to 10 meters, 28,332. There we are. And that's negative 1. Okay, let's go ahead and calculate that out for the single UnUn. So divide this by 2. So that's going to be negative 475. Here that's going to be a negative 4.6. Negative 4.9. Negative 0.50. Negative 0.485. Negative 0.475. And negative 0.50. We will get these insertion losses entered into the spreadsheet, and we'll calculate our efficiencies for these 1002 toroids. From my memory, this is looking very good. I think we're going to be pleasantly surprised with the outcome. So let me get those numbers keyed in. We'll come back and review our results and compare them to the previous tests. Okay, going back to the start of our journey with the experiments on these different transformers, toroids, and capacitors. This was our original, had the two FT24043 toroids and a generic 100 picofarad capacitor that was purchased off of eBay. And we had between 14.1 and 35% insertion losses, which was enormous. And then we changed to the TDK capacitors. And I've got these asterisks above the columns that we need to compare. This is insertion loss columns. Here we had a low of 13.3% insertion loss and a high of 26.5%. So we had up to a 9% change there at 10 meters, and at the 12 meter band we had a 10% improvement in signal just by changing capacitors. Well, then wanted to find out, you know, these both were wound with the 14 total turns, where the first two turns were the bifiller twist, which look like this. This is the bifiller twist, where we got the first two turns twisted together as primary and secondary. And then we got the other 5 turns for the 7 on this side, and then the other 7 on this side with the crossover. This is the way that these two transformers were wound. Then we wanted to try a different type of winding. And then we went using the same type of cores. We went to the single winding auto transformer style of the transformer here, where the windings are tight together, still using the 100 picofarad TDK capacitor, and we tested these two back to back. The results from that one look like this, where this is 14.2 tapped winding, still with the 240-43 toroids, and our insertion losses improved even more. This is the bifiller twisted winding. This is the tapped winding here. went down even more, except right here it went up marginally, went up 0.9 of a percent there, and went up 0.1 of a percent there, but it went down here 2.06, went down here 4.86, and it went down here to 10.22. That is a big change from 26.5 down to 16.2% insertion loss. And, you know, if you're operating in the 10 and 12 meter bands, this was a huge improvement. But now we've got even more changes. Now we've got the different cores. These are the 1002 cores. Let me slide this over a little bit so you can see it. These are the 1002 cores, which are like this compared to the 240-43s here. This is also type 43 material, but it's just a different size and shape of core. They're smaller in diameter, but they're thicker. And that's really the only change between these two. They've got the same type of winding, the same type of capacitors, but it's just a difference in the core. So now we ran these, and it improved even more. Look how flat this is. Notice every one of them starts with a 10. It goes from 10.1 to 10.9. You know, less than 1% variance in the insertion loss across all the bands. That is huge. Huge. So here, we'll go all the way. Let's just compare the ones with the TDK capacitors. Here we had 26% insertion loss. Here we had 10.9%. That is a 15.59% improvement on the insertion loss. So what we're talking about here, on this one you'd be getting, you know, for 100 watts in, you'd be getting 73.5 watts out. Here for 100 watts in, you'd be getting 89.1 watts out. Big improvement, big improvement. And all the way across the band here, this one is so much flatter, has so much less insertion loss. You know, here you've got, you know, everywhere from 13 to 16% insertion loss. All these start with 10. That is phenomenal. So these are the best ones that I know about so far. There may be others out there. If you know of something that's better, hey, let me know. I'd be glad to try to test it. But I don't think you can go wrong by using these. Now this one is set up pretty much for low wattage. You could probably run 100 watts digital through this, and 200 to 300 watts sideband, but I wouldn't go any more than that on a single core. You can stack these cores just like we stack the cores on these here, and you can improve the power handling capacity by doing that. So it's up to you. For 100 watts or less digital, and say 250, 300 watts or less sideband on these single cores should be able to handle that very well. We're going to try to get outside and get these tested, see what our SWR looks like. If you got anything out of this, don't forget to like and subscribe. Okay, we've got our finished 49-to-1 UnUn, and we're connected up to our end-fed half wave, going up about 25 feet in the tree there. We have our Counterpoise here, which is approximately 6 foot 6 inches, which is 0.05 wavelength of the lowest frequency that we're going to operate on, which is around 7.1 megahertz. We're going to first test out with the NanoVNA, and then we'll test it out on the air. This is our 49-to-1 matching transformer using the 1002 toroid with 14 turns tapped on turn number 2, and we're using the 100 picofarad TDK capacitor. We also have our common mode choke so that our counterpoise will work as intended. We have our wire driven element going up into the tree there on that first big limb, which is about 25 feet. We're going to go over to our beast here, get inside, and we'll check out what our SWR is across the bands. Okay, we've got our 40 meter end-fed half wave connected up through our 49-to-1 UnUn that we wound on the 1002 core with the 14-2 turns tapped at the second turn. We want to take readings on this to see what the SWRs read on the different bands. Here we're on 40 meters. We want to get to 7.235 like we been measuring. And there's a 7.235. We got a reading of 2.4 SWR. Now, we have to remember that this is a multi-band antenna. It's not going to be flat across all the bands. There's trade-offs between the lower bands and the higher bands. You normally want to tune these antennas to be the most resonant on the 20 and 15 meter bands, because that's kind of the break point where it needs to be either longer or shorter to raise or lower the SWR. So right now on 40 meters on the 7 megahertz band, we're reading 2.4 at 7.235. Let's go up to the 20 meter band, and we can see here it's a lot lower all the way across, but we need to check it at 14.267, and there's 14.267. We're reading 1.19, which is pretty reasonable, because we kind of have it centered between, or balanced between, the 20 meter and 15 meter. And you notice here it's more resonant towards the lower part of the band, so this one would really like to see it a little shorter to be resonant here at 14.267. So this one wants the antenna to be shorter. But let's go up to the 15 meter band now. Okay, and at 15 meter band we want to look at 21,300. And there's 21,300 right here, and we're reading 1.66 SWR. And it's more resonant towards the high end of the band, as you can see here. As it's getting lower, it's towards the high end of the band. So this one would like to see the antenna longer to bring the resonant point closer to our frequency that is our target frequency. So let's go on up and look at the 10 meter band now. And we'll see our dip here. Let's go to 28,332. It doesn't give us that exact breakout here, but we can get to 28.335. And that changes depending on what your start frequency and your stop frequency is, but we'll use 28.335. That's close enough. But here we're reading 3.16, and where is our marker in relation to our dip? Our marker is way up here. So the resonant point is much higher, so this one would like to see the antenna longer. And that's the same thing that 15 meters wanted to see. Here, since the resonant point is higher, it wants to see a longer antenna there on 15 meters also, whereas here it would like to see it shorter on 20 meters. Go back to 40 meters. And again, it would like to see the antenna shorter to raise that resonant frequency. So that's what I was talking about, where you want to tune it to try to get a balance between 20 meter and 15 meter, because anything below 20 meter, it wants to see the antenna shorter for this particular antenna, and anything above 20 meter, it wants to see the antenna longer. So that's why you need to focus on tuning your antenna to get a balance between 20 and 15 meters. Let's get connected up to the radio and to the SWR meter and take some live readings now. Okay, we've got our radio set up now, and I'm going to start out down on 40 meters at 7.235, transmitting lower power so as try not to interfere with anyone. We're on coax 1. We don't have any tuner engaged. We're in bypass mode, as you can see here, on coax 1. And this is a cross needle, so I'll probably have to read it to you. I've got it zoomed in about as far as we can where we can see everything there. And we'll see what we get on the different frequencies. Here on 7.235, it's reading a little over 2 to 1. So that's about 2.1, 2.2 to 1. I'm going to give it 2.2. All right, so let's go to 14.267. Let's see what it reads. Oh, very low. The needle's not even moving off of 1, so that's 1 to 1. So on 20 meters, it's 1 to 1. And when we were using the NanoVNA, we were reading 1.19 to 1. So it's not even moving. All right, well, let's go up to 15 meters, 21,300. Okay, now we're up on 15 meters at 21,300. Put it in medium power mode. Let's see what it reads. Okay, I'm reading about a 1.9, 1.8, so we'll go with 1.9. And now we're going up to 10 meters. All right, that's 28.332, and let's key it up and see what it does. And that's right at 3.1 to 1. All of these are within the range of your tuner. That most radios going to have a built-in tuner, and you need to, normally speaking, other than the resonant bands that you tune it for, where we're looking at a balance between 20 meters and 15 meters. Anything other than those two, you're going to need a tuner to get the SWR ratio down. That's just the nature of multiband antennas, especially the end-fed half-wave. Okay, the results are pretty much like I expected. We're going to get our best results between 20 meters and 15 meters because that's where the antenna is balanced. We have to kind of balance the readings between those two bands in order to get the best SWR. That way it's going to be flat there in the middle, but on those two bands, and it's going to go up on 40 meters and it's going to go up on 10 meters because like we talked about before, that's kind of the balance point. Anything 20 meters and below wants a shorter driven element, and anything 20 meters and above wants a longer driven element. So that's the reason you have to kind of balance it there. But the SWR ratio on this antenna is pretty much what was expected. As you remember, that was not our primary goal with this type of 49 to 1 transformer. What we were shooting for was higher efficiency. The efficiency on this transformer is right around 90% all the way across the band. You tune out your SWR and more power is going to get to the antenna. And when you get more power to the antenna, you get more signal on the air. And that's what we're going for. This particular single core will handle 250 to 300 watts on sideband and 100 watts on digital. I wouldn't go any higher than those two numbers with a single core in the transformer. If you want to go higher power, double up on your cores, use 2 cores. Then you could go in excess of 500 watts, probably around the 750 watt range with this particular style. Don't know what a 3 core would do. 3 core might work for you as well, but I know the 2 core will work. And you probably want to go with a thicker gauge wire. This is 16 gauge. You probably want to go to 14 gauge, maybe even 12 gauge on your winding in order to handle more power. This is what I use when I go out for POTA or just for remote operations. Very good, very handy antenna. Just sling it up in the tree. You know, I've got it tied off to posts. You don't have to use posts. You can use string and tie it to another tree, whatever length of string you may need to reach the next tree or whatever obstacle you're tying off to. Hopefully this has been helpful. We got good results. It's a good working antenna. I'll put the length of my driven element down in the description. So if you want to try to duplicate this, you can. I'll also put the gauge of wire that I'm using, because the gauge of wire will affect how long the antenna needs to be in order to get this same type of results. If you like what you saw, please subscribe. Leave a comment if you got questions. I try to read all the comments and respond where I can. This is Kilo Mike 4, Zulu Kilo Bravo. Have a blessed day.